Hello everyone, today we will be discussing about this question which came in GATE 2021. The question is the delta O of CrH2O whole 6 3 plus, CrF6 3 minus and CrCN whole 6 3 minus follows the order. So in this question we have been asked to write the order of this delta O for these three given complexes. So here we can see that all the three complexes which are given here are octahedral species. All of them are octahedral complexes. Okay. So we know that transition elements have 5 d orbitals which are dxy, dyz and dxz, dx square minus y square and dz square. In a spherical crystal field, all the 5 orbitals are having same energy. But in octahedral crystal field, this degenerate set of orbitals will split into two sets, T2g and EG. T2g will have dxy, dxz and dyz, whereas EG consists of dx square minus y square and dz square. T2g is having pi type character, whereas this EG is sigma type. The difference between this T2g and EG set is the delta O value. This is also called this crystal field splitting. So this delta O depends on various factors. They are charge on the metal, principal quantum number and ligand field strength. So let's start with comparing this metal charge. So for the first complex given CrH2O whole 6 3 plus, if we consider that chromium is having an oxidation state of X, then X plus, since H2O is a neutral ligand, it will carry a charge of 0 and the overall charge of this complex is plus 3. So X plus 0 is equal to plus 3 or X is equal to plus 3. So in this complex, chromium is present in plus 3 oxidation state. Now for this complex CrF6 whole 3 minus, if we consider this having X oxidation state, then X plus 6 into fluorine carries minus 1 charge each. So this equal to overall charge is minus 3. So X minus 6 is equal to minus 3 or X is equal to plus 3. So here also chromium is present in plus 3 oxidation state. Now for this complex CrCN whole 6 whole 3 minus, X plus Cn also carries a charge of minus 1 and overall charge is minus 3. So X minus 6 is minus 3 or X is equal to plus 3. So again in this case as well, chromium is present in plus 3 oxidation state. So here we can see in all the three complexes, the charge on the metal is same, that is plus 3. So on the basis of this factor, we can't compare the given three complexes. The next factor is principal quantum number. So in all the three cases, we can see that chromium is the transition metal present. It is a 3D transition element. So we can't compare on the basis of this as well. Now next, moving on to the ligand field strength. So here we can see that all the three complexes have different ligands present in them. So this has H2O as the ligand, this has fluorine and this has Cn. H2O is a sigma only type ligand. Fluorine is a pi donor ligand. And Cn is a pi acceptor ligand. So for checking this ligand field strength, if we look on this spectrochemical series, we can see, we know that on going from left to right along this series, that is on going from pi donor ligands to pi acceptor ligands, the ligand field becomes strong. So pi acceptor ligands are strong field ligands, whereas pi donor ligands such as halides are weak field ligands. And H2O somewhere it falls in between. Okay, and it has only sigma only type of interaction with the metal. Cn minus is a strong field ligand, and fluoride, this is a weak field ligand. So if there is only sigma type of interaction between the metal and the ligand, then in an octahedral field we know that the degenerate d orbitals split into T2G and Eg, and the energy gap between them is the delta O. But if we have pi donor ligands like the halides, because of the presence of lone pairs in them, and as they are electronegative, so they lie lower in energy, and because of this field, px and py orbital, px and py are filled if we consider pz, like if we consider the z as the internuclear axis. Then px and py are filled and they have the correct symmetry to interact with the metal T2G set of orbitals, and they a combination of bonding and antibonding orbitals will result from them. So this is the bonding T2G and this is antibonding T2G star. Since the antibonding T2G star has closer energy with that of the metal T2G orbitals, therefore it will be largely metal based, and this is the HOMO. This energy of Eg orbitals will remain unchanged, and as a result of this we can see that in case of pi donor ligands the delta O value is decreasing from sigma only type of interaction to pi donor ligands, whereas in case of pi acceptor ligands we know that here in the pi acceptor ligands they have a vacant pi star orbital. Since this is vacant, so they lie higher in energy, and here also this have suitable symmetry to interact with the metal T2G orbital, and as a result of which a bonding set of T2G and antibonding T2G star orbitals will result. And since in this case the bonding T2G lies closer in energy to the metal T2G orbitals, therefore this T2G set will be highly metal based. And now this is the HOMO. So on moving from just sigma type interaction ligands to pi acceptor type ligands, we can see that here the delta O value increases. Okay. So in this question, we saw that chromium had +3 oxidation state, so it was a D3 system, and therefore we can see that delta O decreases in case of fluoride. For H2O, it will lie somewhere in between, and for pi acceptor Cn minus, it will be the maximum. Now going back to the question, Therefore, CrCN whole 6 3 minus will have the maximum delta O. This CrH2O whole 6 will lie somewhere in the between, and CrF6 3 minus will have the least value of delta O. So option number C is the correct answer. For knowing more about this, please refer to lecture number 35 on coordination chemistry delivered by Professor Devashish Ray from Department of Chemistry, IIT Kharagpur. The link for the video is given here. Please go ahead and watch the video. Thank you.